Hi everyone, I'm Ainesh Bakshi from Carnegie Mellon University, and today I'll be telling you about sample optimal low-rank approximation for PST matrices. This is joint work with Nadia Chaporko from MIT and David Woodruff from CMU. All right, let's get started with a primer on low-rank approximation. Here we're given as input an n by n matrix A and an integer k, and the goal is to factor A into two matrices U times V such that their inner dimension is k. Note, this restricts the product of U times V to have rank at most k. All right, a bit more formally, we can represent the low-rank approximation problem as the following optimization objective. Here we are minimizing over factors u and v such that the distance between A and the product u times v is minimized in squared Frobenius norm. Recall, the squared Frobenius norm is just the sum of squares of the entries. The low-rank approximation helps us obtain a compressed representation of the input matrix. In particular, instead of keeping track of n squared parameters in the original input, we will only need to keep track of n times k parameters in the factorization u times v. It's often used to detect structure in data. It's used for clustering tasks and a primitive statistical modeling and distribution learning. Okay, so let's consider how to solve the low-rank approximation problem. Here we'll use the singular value decomposition, and recall for a symmetric matrix A, the singular value decomposition can be represented as a product of three matrices, Q, sigma, and Q transpose, such that Q has orthonormal columns, and sigma is a diagonal matrix which represents the singular values. Q transpose, of course, has orthonormal rows. Okay, so let's see how to get a rank A matrix out of this. We simply truncate the diagonal entries of sigma to the top k entries by zeroing out all the rest. Okay, if we multiply out these matrices together, we obtain a rank K matrix, which we represent by A sub K. In 1936, Ernst and Young showed that this is actually optimal for the low-rank approximation problem. Okay, so now, since we're computer scientists, we're interested in figuring out the computational complexity of computing A sub K. And there are many algorithms to do this. So for instance, there's a Gillespie factorization which runs in n to the omega time, where omega is the matrix multiplication constant. There's power iteration, which depends on the singular value gaps. And then there's randomized algorithms, which will be the focus of this talk. Following a long line of work on randomized algorithms in 2013, Clarkson and Woodruff showed that you can compute a rank K matrix P such that the distance between A and B in Frobenius norm is at most 1 plus epsilon times the distance between A and A sub K. And recall, this is the minimum possible distance. Further, we can compute such a low-rank approximation in time which is proportional to the sparsity of A, also known as the number of non-zero entries in A. It's also not too hard to see that reading the input is necessary. For this, consider the following example. Here we have a matrix, which is an all ones matrix with a randomly placed entry that is really large, such as this infinite entry placed here. Note, if we do not read the entire matrix, we will not find this really large entry, and any approximation that we come up with will be arbitrarily bad in this Frobenius norm compared to the optimal low-rank approximation. Okay, so let's change gears a bit and consider the PSD low-rank approximation problem. Here we have the same objective as before, but in addition, we assume that the input is PSD. Recall, a matrix is PSD if and only if all the eigenvalues are non-negative, and it can be written as an inner product matrix, so in the form of Q transpose, and all quadratic forms are non-negatives. A motivating example for such a matrix to occur in practice would be an empirical covariance matrix. So let's say you're given an n by d data matrix, represented by capital D here. The empirical covariance matrix is then given by D transpose D. Many tasks for data analysis involve projecting onto the top k subspace of such a matrix. Storing this matrix might require too much space, and thus computing low-rank approximations for such matrices is useful. Musco and Woodruff in 2017 showed the following extremely surprising result for PSD low-rank approximation. What they showed was an algorithm that queries nk over epsilon to the 2.5 entries in the matrix. Note, this is highly sublinear in the size of the matrix, which is n squared, and is also sublinear in the number of non-zeros in the matrix. and outputs a rank K matrix B such that it satisfies this guarantee as before. Further, the running time is linear in n and polynomial in k or epsilon. You can think of the algorithm of Muscoin-Woodruff as follows. Given query access to the input matrix A, it reads nk or epsilon to the 2.5 entries, and based on just reading these entries, outputs a low-rank approximation to A. Consider the special case of this problem where the input matrix A itself is low rank. Then this guarantee implies that reading really few entries in the matrix, we can recover A exactly. Musk and Woodruff continue to show an information theoretical lower bound on the number of queries that you have to make to the matrix. And in particular, they show that a linear dependence in n, k, and epsilon is necessary. In other words, if you query any fewer entries, even with access to unbounded computation, you cannot get a constant approximation to the low rank approximation objective. All right, so let's see a picture of this in action. On the x-axis here, we have the query complexity of the problem. Above nk over epsilon to the 2.5, we know fast algorithms for low rank approximation. And below this threshold of nk over epsilon, we know that the problem is impossible. And the question is, what is the true complexity of PST low rank approximation? One foreseeable obstacle to this problem is a quadratic dependence on 1 over epsilon. And this is as follows. So in all of the known algorithms for low rank approximation, we require using concentration of measure arguments, where we union bound over an exponential number of events, and thus incur the 1 over epsilon squared dependence. So again, it is not clear whether the right dependence is quadratic in 1 over epsilon or linear. Without further ado, I'll tell you our results. So what we show with the Chaparro and Woodruff is that a linear in nk over epsilon query suffice to compute a low rank approximation to A. Further, the running time of our algorithm is n times k to the omega minus 1 or epsilon to the omega minus 1. Recall omega is the matrix multiplication constant, and if omega is 2, our running time is also linear in nk and epsilon. Okay, so let's look at the picture again. Let's consider the running time now along the y-axis. And as we mentioned before, even with unbounded computation, below this threshold, we cannot get any algorithms. And above this threshold, we get a linear time algorithm. In some sense, this is the sharpest possible phase transition. Below this threshold, there exists no algorithms, even with unbounded computation. And above this threshold, there is a linear time algorithm. I'll now describe some applications of our result. Consider the following modification of the problem where we require outputting a PST matrix as our low rank approximation. So here, in addition to A being PST, we want our output B to be PST as well. We show that again, we obtain an algorithm with linear dependence on n, k, and epsilon for this problem as well. Note that this problem shows up in practice for recovering correlation matrices, where the input is a corrupted correlation matrix, and the goal is to come up with a low rank approximation for this matrix. And since it's a correlation matrix, it needs to be PST. Our bounds improve the previous best known algorithm, which incurs a polynomial and k over epsilon in the query complexity, as well as the running time. The next application is for negative type metrics. So here we want to compute a low rank approximation for matrix A, which is no longer PST, but instead a negative type. So let's define that. We say that a matrix is negative type if given a point set x1 to xn. The ijth entry of the matrix can be represented as the Euclidean squared distance between xi and xj. In prior work with David Woodruff, we showed that we can actually output a rank k plus 4 matrix B, which satisfies the rank k guarantee as described here. In comparison to the actual low rank approximation problem, we now output a rank k plus 4 matrix instead of a rank k matrix, and this guarantee is called a bicriteria guarantee. And the main open question in this work was whether the bicriteria nature of this guarantee is necessary. So using the techniques that we develop in this work, we are able to show that the bicriteria guarantee is not required, and we in fact obtain a low-rank approximation for negative type matrices with running time and query complexity linear in n, k, and epsilon. There's another application for ridge regression, which we will skip over given type constraints. Okay, so now I want to give a bit of intuition for why we can actually achieve sublinear time algorithms for PST low-rank approximation. So recall the following instance, which was a lower bound for the general problem, where we were hiding this really large entry uniformly randomly somewhere in the matrix. To see why we can no longer do this, it suffices to show that this matrix is not PST. But also it will give us intuition into why these algorithms actually work. So the first observation here is that the diagonals of a PST matrix form a uniform upper bound over the off diagonals, which precludes such instances. To see this, recall that A can be written as XX transpose for some matrix X. In other words, the ijth entry of A can be written as the inner product between the ith and jth column of X. So here along the diagonal, we have the norm of the ith column of X, and the off-diagonal entries are the inner products between the I and jth diagonal entry. To see why the diagonal entries form an upper bound over the off-diagonal entries, we simply use the Cauchy-Schwarz inequality, which says that if we consider the product of these two off-diagonal entries, then it will be less than the product of the corresponding diagonal entries. All right, with this intuition in mind, I'll describe some new techniques we introduced in this work. We show that we can reduce the low-rank approximation problem to this new problem we call spectral regression. While we do not have time to describe the reduction in its full detail, this problem is a standalone problem which we believe to be of independent interest. Let us begin by recalling the standard regression problem, where we want to minimize ax minus b, but instead of x and b being vectors, we now consider them to be matrices, and we minimize the Frobenius norm difference between them. Spectral regression is the following simple twist to the standard regression problem, where we replace the Frobenius norm by the operator norm. We give a sublinear time algorithm for solving this problem, where we sample rows of A and B proportional to the row norms of A, and then we show that the sketched problem admits a closed form solution, which we can compute exactly. We also show that the sketch problem is a good approximation to the original problem. Note that we obtain a relative error approximation to the original problem without querying a single entry in B. This is surprising since we are solving a regression problem without reading the response matrix. The key ingredient in our analysis is so-called spectral norm decay results. So here the setup is as follows. We have an n by n matrix B, and we sample q rows of this matrix uniformly at random. And the resulting matrix is now this q by n matrix. And the question is simple. How does the spectral norm of the sample matrix compare to the spectral norm of the original matrix? So let us denote the sample matrix by B sub q. In a seminal work by Rudolphin and Verschanen in 2004, what they show is that the expected spectral norm of the sample matrix B sub q is at most square root q over n times the spectral norm of the original matrix, where q is the number of rows that we sampled, and n is the input dimension, plus a logarithmic dependence on q times the largest row norm of the matrix B. This result shows how to bound the expected operator norm of the sample matrix in terms of the spectral norm of the original matrix. We extend this result by showing that uniform sampling is not necessary, and in fact, if we sample rows of B proportional to the row norms of A, we can still obtain a similar guarantee. Note that it is important for us that we are not uniformly sampling, since uniform sampling does not lead to an efficient sketch for this problem. Hopefully, this gives you an idea of the techniques we introduced and inspires you to look at our paper for more details. I'd like to conclude with some open questions and future work. One broad direction of work is to identify more families of matrices that admit sublinear algorithms for linear algebra problems. Some work in this direction considers van der Waals and Henkel matrices, studied by Shi and Woodruff, and Toeplitz matrices, studied by Lawrence, Lee, Moscow, and Moscow. Further, we can ask, how robust are these algorithms that we consider to the assumptions that we make? For instance, if our input matrix, instead of being PSD, is a corrupted PSD matrix, do our algorithms still work? We make partial progress towards answering this question in the same paper. Another interesting direction is to estimate matrix norms in sublinear time. Here we consider the bounded entry model introduced by Balkan, Lee, Woodruff, and Zank, and estimate norms such as spectral norm and shadow norm. Finally, can we test matrix properties in sublinear time? In some upcoming work, we initiated testing PSTness in the bounded entry model with Nadia Chaperko and Rajesh Shara. If you want to know more about this recent progress, Raj is giving a talk on this work as well, and I recommend you to watch it. Thank you for your time.